Hello and welcome to another episode of Isn't That Something? I'm Ralph Crewe, and today we're going to do another long-form podcast style episode. I got to interview a brilliant scientist. I'll tell you more about him in a moment. By the way, this is going to be released as an actual audio podcast. If you haven't already, please consider subscribing to that. You can find it anywhere that you find podcasts. It's just Isn't That Something? Another thing, if you're enjoying the videos that I've been making, please consider supporting me on Patreon. I'll leave a link for that in the description. Support on Patreon is easily the best way to keep me going and allow me to continue making the nerdy videos that I've been making so far. Another note about that, my production schedule has sort of changed a little bit. You'll notice a brief hiatus of the ordinary fast-paced, heavily edited videos. They're coming back. It's just I'm trying to get ahead of schedule on my production. At the moment, I've been producing videos and then publishing them immediately as I'm done editing them. So I'm sort of right on the knife edge of production. That's not a really sustainable way to do things. So I'm taking a little time to write lots of scripts, to film multiple episodes, and sort of get a production schedule that's more sustainable and ideally will be more consistent and make for better content. Now, on to my interview with Dr. Scott Edgington of NASA.
Isn't that something? Isn't that something? Something.
I am absolutely thrilled today to have a conversation with Dr. Scott Edgington, who has been working with NASA and JPL for quite a while on some pretty amazing projects. Scott, thanks for coming on and talking to me today.
Well, thank you, Ralph. Thank you for the invite. This is a pleasure to talk to you about the exciting things that we're doing at NASA.
Yeah, and I mean, of course, NASA has no shortage of exciting things. But before we get into what you're working on now and some of the awesome stuff that you've worked on in the past, I just wanted to get some background on who you are. You know, how you got into this and what you're doing now.
Well, as a kid, I was really interested in studying astronomy, you know, the stars, black holes, things that kids get excited about, you know, exploring space, being an astronaut, etc. And, you know, at that time, I was also interested in physics and chemistry and, you know, math and all of the above, you know, and all the STEM fields that you could think of. And I had some good opportunities in high school to explore. I had a great chemistry teacher, and she inspired us. She appointed me, for example, to be one of her lab assistants, which got me, you know, going down the track of, oh, I want to be a chemist, and and so, you know, all that fun, those fun experiments that you would do in chemistry class.
Oh, yeah.
I got, you know, hands-on experience doing those things. And then physics, you know, started learning physics and, you know, doing all those experiments in high school. And just had tons of opportunity for me as a high school student. But then, you know, you have to choose a college.
Yeah.
And so, you know, I went through all the list of colleges that I wanted to go to, and I chose Pitt, the University of Pittsburgh. And,
Panthers.
Yeah, go Panthers. And you know, and at that time I was thinking, oh, I need to do something practical here. So I went into an engineering program called engineering physics, and that kind of combined my interest in physics with engineering. You know, try to, you know, get involved with something practical. You know, but at that time it was like more like building bridges.
Sure.
And
which
and
in Pittsburgh really makes sense too. If you've been to Pittsburgh, I know you're from
exactly,
the area, so
yes.
you know all about those bridges.
Mm-hmm. Oh yes. And but I said to myself, you know, I had that calling. Yeah, you know, I want to do something different. So I actually got involved with this physics professor at the University of Michigan who launched rockets into the atmosphere. And he launched from Wallops Island, and these sounding rockets explored the Earth's own atmosphere. And that got me interested in studying the Earth's atmosphere, the upper layers of the atmosphere where you
Right.
see the aurora, for example.
So
Uh,
these sounding rockets, these are more than just model rockets, right? You're going up into the mesosphere, but how high up are we talking here?
Thermosphere. So you're
Oh,
talking
wow.
about 100 kilometers.
So actually, like the edge of space.
Yes, yes. Not quite getting into orbit, but yeah, you're reaching those upper layers there where you're
Wow.
sensing the electrons that's coming in from the sun and all that. It's amazing what you could do with, just launch this rocket up with instruments that can measure things like electrons, protons, ultraviolet light, and all that stuff got me so excited as a student, at the university. After that, I decided, I want to study the Earth's atmosphere, and so I looked for programs and ended up at the University of Michigan, and they have a really good atmospheric and space science department. And during that time, I was studying the atmosphere of the Earth. But then that little thing in my head that said, I want to study something a little further out. It just came back and said, the atmospheres of these other planets are equally as interesting as Earth's. And that got me going down the path of exploring the outer planets. And I had a professor who I teamed up with, and my thesis work was actually studying the atmospheres of Jupiter and Saturn, like the picture behind me.
Right, which is such a stunning picture, and we'll come back to that in a minute. But I mean, these are pretty different atmospheres than we see on Earth.
Mm-hmm. Oh, yes. And there's a lot to be learned in their exploration, comparing them to Earth's. How are they different? What's the chemical makeup? How do they work physically? And by studying them, you could bring back a knowledge about the Earth's atmosphere that you wouldn't have if you just studied the Earth's atmosphere.
Right.
And the same thing applies to studying the surfaces of other bodies. We're used to living here on this Earth, and we study the Earth's geology, but what about the other geology out there? Mars, for example, Venus, for example. And so there's a lot of that type of stuff that could be learned. And so back to my own history, I spent 7 years in Michigan. I just loved that place, and didn't want to leave until my professor said, "Okay, well, it's time for you to go." and so I started looking around, and job options came available. I could have been an astronomer in Texas at McDonald Observatory, for example. But then I was like, oh, JPL, that sounds like an interesting place to be. And so I applied and got involved with a postdoc program that they have, postdoctoral researcher program. And I came out here to Pasadena, California, and did that for 2 years, and explored Jupiter and Saturn under the guidance of a professor and researcher here at JPL. JPL is the Jet Propulsion Laboratory.
Right, world famous. I mean, I'm sure that the kind of nerds that watch this channel probably already know, but even the tiny edge cases that don't, yeah, JPL, look it up. It's an historic institution. I mean, just the stuff. Well, I mean, I'll let you continue telling the story.
And so it was actually just about 19 years ago that I arrived here at JPL to do that type of work.
Right.
And so it's just amazing. At the end of that 2-year period, I was saying to myself, where do I want to go now? And I was like, this is the place to be.
Yeah.
I could get involved with missions that go explore all these other outer solar system bodies, inner solar system, even the Earth. JPL does a lot of Earth science too. And so I was like, this is the place I want to be. And so I looked around and got involved with Cassini, which was my first job. And until about 2 years ago, it was my only job here at the lab to work for that project.
So let's pivot over to that, because that is in many ways maybe my favorite unmanned space program ever, and it's certainly one of the most just stunning explorations of outer space, and of course it is of the gas giant planet Saturn, which is, we see that beautiful image behind you. Can you tell us a bit about what Cassini is? Like, how did it get started, and how did it get to where it's going? Well, just let us in on that, because it's so cool.
Yes. Well, I mean, the seed for Cassini came from Voyager.
Yeah.
So back in the 70s and 80s, you had the Voyager missions that went to Jupiter and Saturn and explored those planets. And as those probes were flying by Jupiter and Saturn, all the discoveries from that mission just had the scientists saying, we have to go back to these objects and study them in detail. And you could imagine the Voyagers as being a snapshot. You're just flying by, take your pictures while you can. Roll down your window, take down your picture, take your pictures.
Right.
But that's your last. That's what you saw. And so the scientists started to come up with ideas to go back to Jupiter and back to Saturn and explore those planets in detail. And so from that, you have Galileo exploring Jupiter.
Right.
Obviously, that arrived at Jupiter first. And then you have...
It's a shorter trip, too, to be fair.
Yes, it is. Much shorter trip. And easier to get to. With Saturn, it's a bit further out. You need gravity assists to help you along. And so, and even Jupiter, you need to fly by Jupiter to get you there. And so you're talking at least twice the distance traveled. And so you need...
So how long did it take Cassini to get there from Earth?
It took 7 years to get there.
Jeez.
And so from Voyager, and all that excitement in the early 80s, flying by Saturn, that planted the seed that got the scientists talking to the administrators at NASA and saying, we have to go back there. And by the end of the 80s, early 90s, that seed had grown into announcements from NASA and even ESA, the European Space Agency, to go and explore that planet. And there were originally supposed to be 2 spacecraft built, one to explore Saturn and one to go to a comet. The program was called Cassini-Craft, craft being the comet part. Unfortunately, due to budget cuts during that time period, they had to trim down, and one of those missions got cut, and Cassini survived, thankfully. And so it's amazing how one day I walked into my advisor's office in Michigan, and I had a meeting scheduled with him, and he said, Scott, I can't meet with you now. I have to talk to my congressperson about Cassini because they've canceled it. This is Congress canceling Cassini. And so I knew where his priorities lied. And so I basically went off and did my own thing while he did his part to get it reinstated. And a few years later, it's back, on the books. And so the early starts, as in scientists and engineers gathering, bringing together the project, starting to build the spacecraft, that was all done in the early 90s. And then launch time comes along in 97. And it was like, wow, this thing is being built. It's, on the launch pad, ready to go. And I remember my advisor actually traveling to Florida as I was writing my thesis. And so I couldn't go because I had to write my thesis. And
that's got to have been brutal.
I could have seen that launch, but oh well, I had to graduate.
I guess so.
Yeah.
It must have been a nail biter, though.
Mhm.
You know, watching this project that's got years and years of work from so many people, including yourself, and then sitting on top of a rocket. What's that like?
Well, I've seen the footage, and yeah, it's like, wow, this is a huge device. I think it was 2 tons of aluminum, basically,
Hmm.
and all of that sitting on top of the largest rocket that we had at the time, which was a Titan 4, I believe,
Yeah.
or one of the Titans. Yeah, it was just amazing seeing that launch, and I wasn't even there.
Right.
But I saw the footage on NASA TV, and just amazing to see it. And I could only imagine what it would have been like to be there to hear the roar of the engines,
Hmm.
going off. And many of the colleagues that I ended up working with later, were at that launch,
Hmm.
and they had fond memories of being there, seeing all of their efforts come to fruition as it got off the ground.
Yeah.
And then it took 7 years to get there. So
Yeah. And then you wait
yeah,
for 7 years, and
yeah.
it's not like it's going slow, right? Like these. How fast do you think Cassini was? I mean, I'm sure it's, of course, the
Wow.
speed changes as it slings by Jupiter and things like that. But we're
Mhm.
talking, not hundreds of miles an hour, and not even thousands, but tens of thousands of miles an hour, right?
Yes, I don't know the exact speeds, in my head here, but they were definitely extremely fast. We were going so fast that as we approach Saturn, you have to slow down.
Yeah.
Otherwise, if you don't slow down, you're going to just go flying by, just like the Voyagers did.
Yeah.
So that requires engines to fire, and in order to slow yourself down. And
Wow.
I remember the engine burn being a 90-minute burn.
Wow.
Yes, 90 minutes. And a lot of that was in eclipse. And so as you're coming in to Saturn, I mean, if you look at the picture behind me, uh, you're coming in from the direction that you're looking in, and you have to swing behind the planet, which is where my head is here,
Hmm.
and burn those engines. And during that time, you have radio silence, and so you don't know what's happening in that 90
Ooh.
minutes until it comes out of eclipse, and all of a sudden you get that signal and everyone cheers.
Right.
And just amazing day. That was in 2004. And I remember that day fondly because I was actually one of those chosen to be on stage to MC the show
Oh,
to
cool.
basically friends and family. And it was me and several others involved with this. But we're talking in the audience were literally thousands of scientists and their family members who were there, gathered for that day, waiting that 90 minutes for yay or nay, are we in
Yeah.
orbit? And that was just amazing. And when we got confirmation, this huge cheer went up in the auditorium, and it was just, I mean, it was a tearjerker there at that
Yeah.
time. It's like, wow, we're there.
That's amazing. I
Yeah.
mean, that is a historic achievement.
Mhm.
That team sent this incredible instrument to Saturn, and it got there. It's one
Mhm.
thing to talk
Right.
about sending a rocket to Saturn, but actually pulling it off is pretty remarkable. I mean,
Mhm.
Saturn, what, it's like a billion miles or so. I don't. I
Mhm.
It's very far, very very far,
Yes.
twice as far as Jupiter. Once it's there, what does Cassini settles into its spot? What kind of science is it doing? And I see on your shirt it says Cassini-Huygens.
Yeah.
What's the deal with the Huygens side of things?
Well, one of the ways that we were successful in selling the mission was that we could actually split the cost between us and European Space Agency. And so at the time, the administrators at NASA and ESA got together and formulated a mission and said, hey, we at ESA want to go to Titan. We want to land this probe on the surface of this moon. It's very Earth-like moon. It has a lot of nitrogen and similar chemicals, hydrocarbons, things that you would find in the Earth's atmosphere. And it's just colder,
Like a lot colder though, right?
A lot colder, yes. But imagine if you warmed up that atmosphere, it might actually look like Earth's atmosphere.
Wow.
And so basically the Europeans wanted to go and explore that atmosphere and the surface of Titan. To the naked eye, the Titan's this hazy ball of gas, and very smoggy. And imagine a smoggy day in Pittsburgh or Los Angeles. Now that I'm here in Los Angeles, you can't see the surface, and so you have to send something in order to sample it and see what that surface is like. And so the Huygens probe was designed to do that, and they attached the probe to Cassini, and it was literally piggybacking its ride to the Saturn system. Once we were in the Saturn system, we released the probe, and it was about 6 months after the orbit insertion that we released the probe. Around Christmas time, in fact, we released it. In fact, there's so many things. Orbital dynamics does not care about Christmas.
No.
So there's a lot of things that where orbital dynamics would say, oh, you have this key maneuver to do on that day, and you have to be there working on that day.
Mm-hmm.
So we have so many instances on Cassini where that's been the case. Anyways, I digress. So about a month, not quite a month later, we land on the surface of Titan. And so the probe entered the atmosphere. It actually was on a parachute. So it actually took some time to get to the surface, a few hours. And, along the way, it's just measuring the winds, measuring the particles in the atmosphere, the chemistry of the atmosphere. And then eventually comes to land on the surface. And it just so happened to land in what you would call a drive riverbed here at, in this desert Southwest. Just no liquid, but you could tell it was a region where water had flowed, or liquid, I should say.
Right.
Because water is frozen on the surface of Titan, which should have the viewer asking the question, well, what flows on Titan? And it just so happens, if you pull out your chemistry tables, those chemistry tables will tell you methane is the liquid that could flow on that surface. And so you're talking about an environment of flowing methane rivers.
It's amazing. Like you think about, like you can go spend some time on a riverbank or even a beach here on Earth, and you could do the same thing on Titan, except for it would be methane.
Mm-hmm. Exactly. And the ice that you're familiar with is rock.
Yeah.
And then it's just like hard. It's not going to melt.
Right.
It did melt briefly, though, when we did land, because the probe was hot enough to reach temperatures that allowed water molecules to, come out into the atmosphere.
Really?
For a short period of time. Yes.
Wow.
Mm-hmm. Yes. And we have, the mass spectrometer measured molecules in the atmosphere that would not be present if it wasn't a warm body sitting on melting ice. So, yeah, really exciting.
That's a stunning thing. And Titan in general is one of the most interesting places in the solar system. And later on, I definitely want to come back to it because there are more plans I know that NASA has in store for Titan. But there are other moons of Saturn that I want to talk about while we have time. And of course, you know where I'm going with this. I see you smiling. Of course, I want to talk about Enceladus and the work Cassini did with that moon. So can you tell us what Enceladus is all about and how Cassini studied it?
Okay. Well, going back to the Voyager days, scientists at the time had evidence that this was an interesting body. We didn't quite know exactly why, but it had a really bright surface, meaning that it wasn't contaminated by, say, meteorites hitting the surface, which causes these surfaces to look dirty and old. It had a lot of fresh surface ice on that surface. It also was sitting in a region called the E-ring, and if you see the bright blue outer large ring here, that's the E-ring. And the E-ring is composed of tiny little ice grains. So, just tiny little ice particles floating around, micron size. You could actually only see it at extreme angles like this, where the sun is behind you. Kind of like if you're driving with the sun in front of you and you see your windshield if it's dirty, it gets all bright. I call this effect the dirty windshield effect. That's really what it is. And so, with your own eyes, you really can't see it when the sun is behind you, but you could see it when it's in front of you. And so that's how tiny these particles are. And so Enceladus, we knew that there was some connection there between Enceladus, which is sitting in the heart of this ring, and the ring itself. And so fast forward to Cassini, during one of our flybys of Enceladus, and we had many flybys of the moons in this system, many of which involved Titan, etc. But we had a few early on designated to go by this tiny little moon called Enceladus. And as we were flying by it, we detected a deviation in the magnetic field. And that magnetic field deviation got scientists to think something's happening here to cause that effect. And we want to explore that further. And so you can imagine, when scientists discover something like this, they're like, okay, what could we do to the mission, to get us closer? We want to view that surface. We want to measure things with our magnetometer, our mass spectrometers on board. We want to look at this in detail. And of course, the engineers are like, oh boy, how are we going to get closer? Is it dangerous? All these things go through the engineers' heads, and trying to figure out how to do this and to do it safely. You don't want to fly into the object. And so is there an orbit that will take you close enough such that they feel comfortable? And so that there was this huge effort to get us closer to this tiny little moon. And when we did that, we took images in that second flyby. We trained our instruments, tuned them to whatever we thought we should be measuring or could be measuring. And sure enough, we flew through one of the plumes of Enceladus. And that was just exciting. It's like, wow, there's a geyser here. This tiny little moon, out of its surface, there's cracks in the surface. And out of those cracks are coming these ice particles, maybe it was liquid underneath, and these ice, it's coming out, it's freezing really quick and becoming ice particles, and we're sensing that as we fly right through. And of course, the whole, after the prime mission with Cassini, which was 4 years, by the way, they actually designed a series of orbits that would study this moon in detail. And of course, several of them were designed to fly through that plume several more times. And each time we learned something different. We got better at what we were doing, tuning our instruments, making sure that we were measuring the right thing and in the right way. And the chemistry of this material coming out, we were seeing salts, we were seeing ammonia, we were seeing methane, CO2, carbon dioxide, just all these materials coming out of this moon. And you wouldn't expect this. I mean, you would expect to see maybe a ball of ice
Right.
with some cracks. But here it is, an active moon.
So what
You
does
know?
that tell us about what's going on underneath the ice at Enceladus?
So one of the most exciting results from these flybys is the measurement of silica as we flew through the plume. And silica is one of these, it's basically grains of sand on a beach.
Mm-hmm.
That's what we are familiar with as we walk through sand on the beach here in, Southern California. And so it's like, how is this material there? And imagine you have this moon. You have maybe a rocky interior. You have maybe a liquid ocean underneath. And you have this icy shell with cracks. And so that silica grain has to travel from this rocky core into outer space.
So
And
something is putting a bit of oomph behind the silica, right?
yes. And so something has to form it. And that's when we learned that there is actually a liquid water ocean tied together with this rocky core. And you could think of a percolator where you have some circulation going on between that ocean and that core, and it's generating these silica grains. And then the cracks in the surface, you can imagine that as a pressure cooker situation where you have a lot of heat and pressure underneath. And that has to be released somewhere. And it goes through the weakest points, the cracks. And so those cracks open up, geysers come out, and we measure it.
Wow.
It's free samples. Yeah.
Yeah. And you've the fact that Cassini actually flew through that material. Just that's stunning stuff. And of course, that means that Enceladus is then one of the most exciting places to explore in the future for possible signs of life, right? I mean, when we talk about life on other worlds, we look for water and some sort of energy source, and it sounds like Enceladus has lots of both.
Yes, if you think of a triangle, you mentioned two parts of the triangle: water, liquid. There's a lot of ice out there.
Right.
There's a lot of gas out there, but liquid water is special. You have that small temperature range that you're looking for there, and then energy. You need an energy source. Life requires energy, whether it's sunlight or heat energy. And here's this moon having two of them. The next thing is the chemistry.
Right.
You have the chemistry. Do you have the carbon? Do you have the nitrogen? Do you have the oxygen that need to come together to form amino acids? Maybe DNA, maybe, amoebas, maybe whales under the surface. Who knows?
I'm sure there are Star Trek fans that would flip out if there were whales.
Yes, I would love it. Anyways, we're very interested in exploring this tiny little moon. One of the paradigm shifts from Cassini was the fact that these tiny little moons could harbor liquid oceans underneath their icy shells,
right,
and be places where we could look for life. It used to be that you thought of the Goldilocks zone as that magic zone between Venus and Mars. Earth just happens to be right in the middle, and that's where life exists. But with Cassini and the discoveries that we made with Cassini, it's opened up a new place to explore.
Right.
And similar with Europa orbiting Jupiter. There's a lot of interest in going to that moon, which also has interesting features on the surface, and we know a liquid ocean. Not confirmed yet, but we hope to confirm that with the Europa Clipper mission, for example.
Right.
So just amazing world out there, just a billion miles away.
Just a short billion-mile jog down the street. Now, if you're going to talk about exploring Saturn, you can't not talk about the rings. Can you tell us a little bit about what Cassini saw? I don't know if you can maybe even show us some images of what Cassini saw of the rings and how they work, and some of the way that the moons within them stabilize them. I've heard you talk about this before, and I get giddy when I hear it. So just let us know what's up with the rings of Saturn.
Yeah, I could send you some images and movies of what you're talking about. Right now, I'll describe using the image behind me. So the rings of Saturn are predominantly water ice, 99% water ice, with some contaminants. So imagine them as ice cubes floating around, or icebergs floating around Saturn in its gravity field. And so you have this complex interaction of a range of particle sizes, from small to large. And so all these particles are coming together, forming structures, maybe crashing together, making smaller pieces. We have some evidence that the moons within the rings are coalescing materials and becoming bigger over time. It's a slow process, but it's happening over time. We've seen evidence that these tiny little ring moons that orbit within probably started as a tiny little particle, maybe an iceberg size thing, that just started gravitationally pulling in more material, and all that material starts sticking together, forming a moon over time. And
it's snowballing, and actually made out of,
yes,
almost made of snow.
exactly. And so and all of these moons, if they get big enough, they're going to create gravitational signatures. And so a lot of the structures that you see within the rings are influenced by, one, the moons within them, creating gaps, causing some flow of material as the gravity of these moons interact with other particles. And also the other moons outside of the rings, like Titan, Rhea, geez, I'm spacing on, there's so many moons.
There are. How many moons do you know?
Tethys, yeah. More than 64 last time I counted.
Yeah, and I know it's one of those numbers that you can learn, but don't worry about remembering it forever, because it's changing, right? We keep finding more and more moons around Saturn.
Yes, the question comes up: what defines a moon? And
right.
So, some moons we envision as being large, like our own, but other moons could be as small as a few kilometers.
Right.
And so, what defines a moon? And so we're discovering these building blocks of larger systems all the time within Jupiter and Saturn's system. Anyways, back to the Saturn's rings. You have all these complex gravitational interactions, which cause waves to form in the rings. And these waves, if you look at them on the surface, they kind of look like a record, LP record, with all the grooves in spirals around Saturn. And so all those waves or spirals are caused by the gravitational interaction with other moons in the system. And it's amazing, mathematically, you can map out this moon causes that wave.
Wow.
And it's just amazing how scientists can piece together that, here's the source of that wave that you're seeing, way over here. Gravity, it works. And so at the same time, we're seeing structures within the rings, waves that can't be explained by the other moons. And when you ask yourself, where is this coming from? Well, you have that big ball of gas in the middle.
Right.
and as things flow within it, you get non-uniform motions. And that causes gravity differences. And those gravity differences are reflected in the signal that you see in the rings.
So you can learn about what's going on in the interior of Saturn by looking at the rings.
Correct. Yes.
Wow.
You can think of the rings as a seismometer.
Wow. That's
Yeah.
pretty spectacular. So what about that big ball of gas in the middle? What have we learned about that?
Well, this kind of ties in with the end of mission. Uh, at the end of the mission, we were interested in getting closer and closer to Saturn. And one of the goals was to measure its gravitational field and its magnetic field and learn something about what's going on inside of it. Is it a solid core? Is it a liquid core? Is it, or somewhere in between? It could be your imagination could run wild with a lack of data. Okay. And so what we wanted was the data.
Right.
So, let's pin down what's happening inside. And so we designed a set of orbits at the end of the mission that got us really close. In fact, so close that we went through the gap between Saturn and the rings.
That still stresses me out that you guys actually did that. That's like threading the needle, and it's. I mean, how did you know that was even possible? How couldn't there have been big chunks of stuff in that gap? Like, how do we know it was even empty?
So there's certain lines of evidence that you have, and since you have a spacecraft with cameras, for example,
Well, yes.
that you could use images of that region to place limits on the size of materials in that gap and also the density of materials in that gap. And so you have that as evidence. You also have magnetic field effects. For example, you could measure the radiation belts around the planet, and you could infer that, well, it has to be relatively clear. Now, that's not saying that there's that one chunk of ice that's there that you're going to fly into. And once you fly into that, your mission is over. Because you're going so fast. And momentum is mass times velocity.
Right.
And so even a small chunk of mass going at those velocities will tear through your spacecraft. And so the engineers were really sweating bullets about this. They
imagine.
like, oh, this is not possible. We need to study this and determine what's the probability of us hitting something on the way through. And so the engineers, they did those studies. At the same time, you have the engineers saying, well, is this possible to begin with? And this is where the NASA navigators who fly these missions, they're really good at determining where spacecraft could fly. And so they determined that there was a set of orbits that they could use to put us on a trajectory to take us through this gap and literally thread the needle, as you put it. And we determined that was possible. It was also a joint study with Purdue University, where the students there in their navigation program, orbital dynamics program, they took part in this study. So this was a time when we could partner up with students, actually.
That must have been so
studies.
thrilling for those students to be part of something like this.
Oh yes, they got several papers out on it, and I mean, you get some recognition there.
Yeah.
And of course, the people at JPL, they're like, okay, well, let's look at this in a little more detail to make sure, kind of polish the cannonball and see what we could get out of it. And so we determined that we could do it. And as one of our proposed end of mission scenarios, we said, okay, well, we have to dispose of the spacecraft, and this is a way we would like to do it. Another idea for disposing of the spacecraft was, well, let's just toss it out of the Saturn system or put it in orbit, that where it would orbit for like 500 years. But Saturn would be this small speck in the center. And it's like, where's the fun in that?
Yeah.
So it was decided this is what we should be doing with this spacecraft, maximize its science in the Saturn system. And so we set it on the course for this end of mission. and we flew through this gap. Oh boy, over 20 times. Just
Wow.
amazing that, and the first time around, and the second time around, and the third time around, and up until the last moment, we were still sweating bullets. Can we do this safely? And once we did the first time, people calmed down a bit and said, "Okay, we did it. Yeah, this is we actually threaded that needle, and now let's do it more."
Wow.
And so we designed that set of orbits that eventually took us into Saturn's atmosphere. But along the way, we measured the gravity, we measured the magnetic field in detail, we measured the particles surrounding the planet, the ring particles falling into the planet. Imagine some of those ring particles just like raining down onto the
Wow.
atmosphere. We actually measured those um, during these orbits. It's just amazing. Of course, those studying the rings were like, "Hey, we have to look at these rings in detail,"
Yeah.
and so we want to look at how close can we get? Can we see an individual ring particle? That was the hope, but with our resolution, unfortunately, we couldn't. We would need a much higher resolution camera in order to see an individual ring particle, but we could still see structures. How do these particles line up to form larger structures? And so we did see that, and just amazing. Some of the most beautiful images of the mission, I think, came from that part of the mission as we got up close and personal to those rings. And even the planet itself, you have the planet in the middle there. You're measuring the gravity, which is telling you something about the interior. One of the big questions was, well, the winds that you measure at the surface, how deep do they go?
Right.
And with the gravity measurements, we've determined they go quite deep, about 1,000 kilometers deep into the planet, and that's just from gravitational measurements.
Wow.
It's amazing that we could determine that. Um, and then one of the most interesting and perplexing discoveries was that the magnetic field of Saturn is almost perfectly aligned with its rotational axis. And if you ask a person who studies magnetic dynamos, they will tell you that this is impossible. It breaks some law of physics that you have this happening. If you look at Jupiter, if you look at Uranus, Neptune, all those magnetic fields are not aligned with the spin axis.
Right. Even our own on Earth isn't
Correct.
aligned.
Mm-hmm. Right. And so what is going on to allow this to happen? And so that is a mystery to this day, that, as to why that's happening. There's some hypotheses out there trying to explain it, but we haven't really stumbled upon the, most convincing reason for it. But it could be something happening inside. Maybe there's a phase transition where you have metallic hydrogen forming somewhere, and that is somehow influencing what you see outside of it. It could be that inside, maybe it is tilted. We're just seeing the outer surface of it. So that's one hypothesis. There's probably a few others that someone that plasma physicists are studying to try to explain this. And so and then it's like, what could you learn from this in terms of constraints you could place on the structure of Saturn? Is it rocky inside? Is it slushy? It might be slushy. Who knows?
It's a big slushy.
Yes, right. Could be a liquid. Is there a liquid layer? It's anyone's guess. But who knows what happens at those extreme temperatures and pressures. And then with those results, you compare those with Juno. Juno is coming back with some amazing knowledge about Jupiter's interior. And so you could basically compare the two and say, how are they alike and how are they different? And that's just exciting to me.
So I don't understand how it couldn't be exciting to everybody. It's really remarkable stuff. And Cassini, I'll make sure to include lots of links to further pieces of media that people can explore and dig into the data. I really can't recommend exploring Cassini enough. It's one of the, if not the most beautiful and certainly compelling scientific programs I've ever seen. But after such a glorious start to your career, you came down to Mars. So you didn't come all the way back down to Earth, but you did move on to working a little closer to home, and now you're working on the Mars Insight program. Can you tell us a bit about that?
Well, my journey took me from the operations world on Cassini with a short stint of science management in there. I was actually the deputy project scientist of the mission, and for about 5 years. And so, and then after that, you have the mission ending, and that end of mission came by, and that was definitely very emotional. And at the end of the day, it's like, okay, the mission's done, and have to move on to the next world out there. And for a while, I was like, okay, I think I'm just going to focus on my own research, which is atmospheres of the planets. So I did a little of that for about a year and a half. And then it was like, okay, I think I'm ready to venture, to a different world. And an opportunity came up with the Insight mission, and they needed basically people to do their science planning. And so that takes me back to the operation world where I started on Cassini. And so it's like, okay, I could do this job. It's just that it's a much faster pace. With Cassini, to put it in perspective, we are designing sequences, basically programs that operate the spacecraft on a monthly basis. And so we have one chunk of time. We're doing science observations for that month. Well, on Mars, it's much quicker. We're designing things for a week at a time or less. And so there's some days where it's like, okay, you start your day, you start planning, and by the end of the day, you have something that's going to the spacecraft. And that's a very fast pace compared to the leisurely pace that we had on Cassini. Now, that said, there was a lot of work to be done during that leisure time, but same amount of work, just really compressed for Mars. And so, so on Insight, Insight is a mission that is designed to sit on the surface of Mars. It has a seismometer, and it has a heat probe that is designed to bury itself into the surface. And so these are the two instruments that are used to study the interior of Mars. So we're interested in knowing what goes on underneath. And when you have something sitting on the surface, well, you want something to measure how much is Mars shaking. That tells you something about what's happening inside. Here on Earth, we have earthquakes all the time. And we learn something about the Earth's interior with every additional earthquake. That tells us something about how rock is moving around inside, how liquid magma, lava, is flowing inside of the Earth. And the question is, how similar is Mars to that, our experience here on Earth? And so, this seismometer, it's designed to provide those answers. So it's a single seismometer. It's sitting there, it's measuring all these quakes, and we've measured well over 300 some quakes since we've been sitting on the surface for going on 700 days now.
Wow.
In 2 days, it will be 700. And so we've measured earthquakes almost on a daily basis. And we've measured about 10 of them in the 3 to 4.0 range on the Richter scale. We're still waiting for that big one that will help us to probe very deep into the interior. You could think of earthquakes as like a bell. Whenever something moves inside the planet, it causes the bell to vibrate. And the surface of Mars, in this case, is that bell, and we're sitting on that bell. And so every motion we can measure with this seismometer. In addition to that, we have this heat probe, which is literally designed to drill itself into the surface. It's more like hammering itself into the surface. And that is designed to get deep enough, about 5 meters, into the surface so that you reach the area that is not influenced by the sunlight. You can imagine if you have a surface heated by the sun, that surface is going to get hot, it's going to get cold, depending on whether it's day or night.
Right.
So you want to be below that effect.
Sort of like how here on Earth, if you're in a cave, it's always the same temperature all the time.
Exactly. Yes. And so you want to know what's the heat coming from the lower levels of that surface. And so this probe will basically provide a temperature thermometer, series of thermometers that will tell us how this heat flow is coming out of the interior of Mars. And then we'll also learn something about the soil properties of Mars as we bury ourselves into the surface.
Literally bury. That's yeah. That's
Yes.
So when it comes to Mars, I feel like this is always one that's interesting. Something about the outer planets, they're so enormous and epic. Like, of course we need to send things there, but like, why send stuff to Mars? Like, why is it, I do believe it's very important to send things to study Mars, but why do you think it's worth it to send missions like InSight and some of the other missions that are coming up to Mars to check it out?
Well, Mars has always been fascinating to us humans. As far as I think the earliest science fiction novels that you could imagine that we know have been written, have Mars somehow associated with them. H.G. Wells, being most famous. So we're always looking out and exploring and wondering what's out there. And here's this planet that has a surface. You could kind of see it in a telescope with, that you could buy, here these days. You could image it with a good camera. And of course, if you have a better telescope, you could see the actual surface. And so there's ice caps, there's places where we think water has flowed before. And there's also questions about, okay, well, if Mars is like this and Earth is like this, how did Mars get to be the way it got to be? And how did Earth, evolve in comparison? And then toss in Venus there, it's like, well, there's Venus on the other side. How did it get to its present state? Did these planets start out the same, or were they different to begin with? What influenced their evolution, both atmosphere and surface? And so I think Mars is an interesting example where we look out and we see something that is very similar to what the Earth's surface might look like, maybe in the desert Southwest or something. And then the polar caps, it's like, well, there's ice caps there. What makes up that polar cap? Is it water? Is it CO2? We know this, most of the atmosphere is CO2. And so we're interested in exploring those regions. And then there's always the desire to, what's the next place to visit other than the moon? And Mars is one of those places that is relatively accessible.
Relatively, yeah. It's still millions of kilometers out there.
Yes. Venus, on the other hand, well, yeah, we could access it, but it's covered by this really thick poisonous atmosphere.
Yeah, that
So
does make it a little harder.
yes, right. And so Mars has that attraction. And when you ask the question, well, if water originally flowed on the surface, where is that water now?
Right.
Is it below the ground? Is it evaporated from that surface? We're interested in knowing those answers. And if you find liquid water on Mars below the surface, well, that's going to be exciting.
Right.
'Cause who knows what's in that water?
Right.
You could have life forms in that water, and that really gets people excited about it. And scientists obviously want to go and explore. Ask the questions: did life exist? Does it still exist? Will it ever? Will it exist in the future? And so and then if we send colonies there eventually, we're going to need that water to survive.
For sure.
We can't take everything with us, and so we have to find it there. And so you want to know, is that water available for drinking?
I might want to put it through a Brita filter at least once or twice.
Yes, definitely.
Yeah, it's so fantastic. It's inspiring stuff. And InSight is, of course, paving the way for other future missions to Mars. We don't have a ton of time left, but I want to hear more about what you have to say about things like the Mars Perseverance project that's coming up. It's on the way. It's in space right now as we speak, and then other cool stuff that's coming up from NASA.
Yeah, Mars Perseverance is more than halfway there. We reached the halfway point about a week ago.
Nice.
And just so exciting. And I could tell the team is very stressed, because we have to get there. We have to make sure it gets there and lands safely. And, all these tasks need to be done getting there. But we should land middle of February. We should be there and hopefully sitting on the surface of Mars and collecting samples. And so the mission is designed literally to collect. You basically go around and say, oh, that rock is interesting. I'm going to pick it up. I'm going to put it in a test tube and leave it on the surface of Mars for another mission to come along to pick it up. And so it's a very ambitious mission. The thought that you could go and collect these samples to begin with and wait for that next mission to come along to go pick them up, very ambitious. But that's part of the Mars program. They have this course plotted where they have missions in mind to go and retrieve those samples and bring it back to Earth. And that's going to be
blows
so
my
exciting.
mind.
Yeah. It's probably going to be a good decade or more from now, but it's going to be so exciting to do that. And it's just amazing when you think of it, what we could do. We're testing new technologies.
Right.
There's we're flying, basically it's a technology demonstration that we could actually fly something in the Martian atmosphere. Thin as it is, we think we could fly this helicopter on the surface of Mars. And so there's a helicopter called Ingenuity, and we'll see if it works. And
we'll see if it works. That's great.
Yeah, I mean, literally, it's there to demonstrate that this is possible.
Yeah,
and I'm sure we're going to learn a lot of things from doing that, both engineering-wise and science-wise. And who knows what the future may bring for Mars. We may be flying airplanes in the Martian atmosphere at some point in time. Who knows?
Yeah.
Which reminds me, we have missions being designed going to Titan. Titan, there's a mission called Dragonfly. And Titan has this really thick atmosphere. So it's very different from the Martian atmosphere. And we know that we could fly helicopters and et cetera in environments like the Earth. And
Mhm.
so it's like, okay, well, let's fly a quadcopter there. And so
It's
this mission
amazing.
is designed to have a well-equipped, scientifically equipped quadcopter that is literally designed to land on the surface, do its thing, uh, collect science samples, and then lift off again, go to that next target. So can you imagine, getting those images back and saying, "Hey, look at that riverbed over there. I want to fly over there and see what's in there." And then you might see a sand dune, ice dune, and so let's fly over to the ice dune and see what's over there. Collecting your samples, doing your measurements, whether it's, and that also has a seismometer on, by the way. See if there's tidal quakes. Um,
Wow.
yeah, just amazing what we could do with this. So that should be arriving in 2027 if things goes as planned.
That's a
And
pretty spectacular program. And it sounds almost like science fiction when I hear you describe it. It gets me excited, and I'm sure there's got to be generations of young scientists and engineers to be who hear about programs like this, and it gets them just sort of jazzed up about it. And for those people, and for anybody, how can people learn more and maybe even get involved in programs like this, in the planetary exploration programs that NASA has?
Well, there's a lot of things like internships that, if you're in college and such, you can get involved with internships. But the average citizen can actually get involved with actually taking part in studying data that comes back from a range of missions, telescopes, etc. A good example is the Juno mission. That's taking a lot of images with this camera that was designed with the public in mind. And so the public is actively involved with determining what they're going to take pictures of and studying those images that come back. And so that's one example where citizen science has become a part of that mission. There's also other types of citizen science programs involving analysis of solar system data. It doesn't have to be images. It could be temperature data on Mars. It could be, whatever data you could think of.
Mm-hmm.
Someone has a need to analyze that data. And programs have been designed to get the average person helping out with that. It's kind of similar to the SETI program, if you remember, where people use their home computers to help interpret SETI data.
Mm-hmm.
But this is a little more hands-on, a little more developed, and you're actually interacting with real scientists who are interested in studying that data. And there's this one really good organization. It's called
Mm-hmm.
Zooniverse.org. There's a lot of examples there where you can get involved as an average person doing science. And I cannot stress how exciting that could be. Imagine, if you have kids or you are a kid, actually looking at real data and making discoveries, helping scientists, study these bodies, and who knows what's out there to be discovered. It's just such an amazing time to be doing science with what we have on our phones, cell phones, laptops, etc. It's just amazing time to
Absolutely.
be involved with science.
Well, totally remarkable stuff, and I'm always inspired. Thank you so much for taking time to talk to me. I'll leave links to a lot of the awesome things that we talked about today. But Dr. Scott Edgington from JPL, legendary Cassini scientist, current Mars Insight scientist, and who knows what the future holds. Scott, thanks so much for coming
You
on.
never know, and I'm always looking out there, and I encourage you to look out too.
Huge thanks again to Dr. Scott Edgington for taking time out of his day to talk to me about the amazing programs that he's been part of in his career and continues to be part of, and just all the awesome stuff that NASA is up to. Those folks really have a good thing going on, I think. I will leave links to all of those programs in the description to this video and podcast so that you can check it out, dive a little deeper if you'd like. Also, I will leave a link to the Patreon for this channel. That's easily the best way to support me. And even a small donation makes a really big difference, makes it a lot easier for me to keep doing this stuff. I'm having a lot of fun. I hope you are too. That's all for now. Thanks for watching, and explore the world responsibly.
Isn't that something? Isn't that something? Something, 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 something.